Okay. So remember that we're talking about we're now working in inferential statistics. Inferential statistics mean we're going to take a sample from a population and we're going to deduce things about the population from the sample. So we're really totally focused on what's the population mean, right? What's the mean of a population based on sample, right? So what we saw was if we could get a point estimate by taking a sample and if we do the mean of the sample, that's a point estimate for the mean of the population. It's like our best guess, right? If we just have one sample and we take the mean of that one sample, well then that's the best we know about what the population is. But then we said we could also develop a confidence interval around that point estimate. So that's what this was about. Okay? So remember we talked about confidence intervals of 90, 95%, and 99%. And let's just review, what did we get for z-scores for those? 90%, plus or minus, yep. So that was plus or minus 1.645 standard deviations. Was a confidence interval of 90%. And then 95%? 1.96, right? And then 99%? Plus or minus 2.575. And these are z values, right? So these are z's, or numbers of standard deviations. Okay, so this approach was when we knew the standard deviation of the population. Here's the key to this. For able to use these z-scores, we knew what this was, right? So sigma known, and that's the standard deviation of the population, right? When the standard deviation of the population is known, then we could use the standard deviation of our sampling distribution. Remember that was that sigma divided by square root of n. And then we could form these confidence intervals based on how much confidence we wanted. Okay? And if we want more confidence that we have a range that the population mean is in, does that mean less precision or more precision? If we want more, we want a wider interval, more confidence that we have an interval that mu is in. Will that be more precision or less precision? Less, because it's a wider interval, right? So if you want more confidence, you lose precision. If you can accept less confidence that your population mean is in the range, then you've got more precision. Okay, so this is how then we figured out what the max and the min of those confidence intervals were, right? Okay, and then we talked about margin of error. Margin of error was half the length of the confidence interval, or the length from our point estimate out to the max, or the point estimate down to the min. So this was E, and this was the margin of error. Okay, so what part of this formula right here is the margin of error? So looking at this formula for finding the max, what part of this would be equal to the margin of error? Would it be just this? Would it be just this? Would it be this times this? Would it be the whole thing? What part of that formula right there gives us half the length of the confidence interval, or from our point estimate out to the max. That distance, that's the margin of error on the confidence interval. Yeah?
Just be the middle.
Just the middle. You mean this number here? Yeah. So he's saying just the z-score would be the margin of error. Is that right? So I think you guys are saying the same thing. You want the z times the standard deviation of the sampling distribution. Everything but the mu. That's what it is. All right, so I'll do that in red. Okay, so it is. It's like the z, but it's in the units of our variable. Okay, the margin of error is in the units of our variable. So if we were doing, lengths of cow legs or something, then it's going to be whatever that is, inches or centimeters, or however they're measuring the length of the cow's leg. Okay, so. Yes, so it's going to be in standard deviations, but then in the units of our variable. How far we are away from the mean. So what I put in red is E. And then notice that, do you need to know what mu is to know what E is? And that was the last problem we had on Monday, remember? It tripped some of you guys up. It's like, well, we don't know the mean. How can I do this without the mean? We don't need it, right? Because it's the distance from the mean out to the max, or the distance from the mean down to the min. So this is our margin of error. And then 2e is the length of the interval, because we go e above and e below. And that's the length of the whole confidence interval. Please.
So that z little squiggle divided by 2, that just means z-score?
That's the z-score for a particular confidence interval.
Okay.
We figured those out on Monday. So these are the most common ones. And so you don't have to go back to the chart and look at these. We can just make note of these and use these. But you should also know, like if I said, find a z-score for an 85% confidence interval, you should know how to do that, right? You should know how to do that. You would take, half of 0.15. So the alpha then would be everything not under the curve. For 85% would be 0.15. And so then what would this area be here? So the total here is 0.15. So then this would be half of that. I think it's 0.075, right? 0.075, and that's where you would start. You go to the table for the z-scores to get what that z value is. If this was 0.075, or this was 0.925. Okay, so that's just a quick overview. Okay, so that's review. Questions on that? So again, what are we doing? We've got a sample, we get a point estimate for the mean, we find the sampling distribution, standard deviation, and we have a z-score for a certain amount of confidence, and from all that information we can build a confidence interval. We can say we are 95% confident that the population mean is between this and this. So was that 19 times out of 20? We'll be right. 19 times out of 20 that we build a 95% confidence interval, the actual population mean will be in that interval. Only one time out of 20 will it fall outside. We'll get so it's like, when it falls outside, it's like we got a very, we got a kind of a weird sample that had like lots of data that was way too low. All right, or we got lots of data that was way too high, and that's just going to happen once in a while. So if you've got a 95% confidence interval, that'll happen about 1 out of 20 times, or 5% of the time. Your sample was kind of just off from the real population, just because that'll happen once in a while. Okay. Questions on that? Okay, so then there it is again. So there's our confidence. Here's our confidence interval. from the min to the max, and then here's our margin of error. And remember, this has to, so we have to have one, these are the conditions that have to be met. Simple random sample. So either we have to have a normal population to start with, or if we don't, we need a sample of like 30 or more. Remember that? It doesn't have to be normal as long as you have a sample of 30 or more. If you have a normal population, the sample can be any size. Okay? And this is when we know, all this was for knowing the population standard deviation. Okay, so again, here's just the same thing again. Illustrating that margin of error would be this part of this, right? So we got a point estimate plus the margin of error gives us the max, the point estimate minus the margin of error gives us the min of the confidence interval. And so if we take a look at this, we really have we have our confidence level, which is our z-score. Okay, and then we have the amount of precision. So we said if we want to increase our confidence level, what happens to the precision? So if we want to say go from 90% confidence to 99% confidence that the population mean is in our interval, then what happens to the precision when we do that? We need a wider interval, so we have less precision. So now what if I said I want to maintain let's see, I want to have a higher level of confidence, but I want to maintain the precision. So I don't want my precision to go down, but I want to be more confident. So I want to keep my margin of error the same. Okay? But I want my confidence to go up. I want to get more confidence, but I want to keep my precision the same. How could we do that? Is there any way we could do that? So I don't want to increase my precision, but I want more confidence. Something else needs to change. What would have to change to do that? What's that? What would I need for the sample size? Yeah, so if I had a bigger sample size, I could get more confidence for the same margin of error, right? The larger your sample size gets, what happens? That standard deviation shrinks, okay? So if I could get then I would have room to keep, increase my confidence. Okay, so there's these relationships between confidence level, precision, and sample size. If the sample size goes up, then I can get more confidence for the same amount of precision, meaning I can keep that margin of error the same and be more confident that the population mean is in my range. Okay, so this then motivates the idea of how big of a sample do we need for a certain confidence level in a certain situation. So it would be nice to be able to know what n is in a certain situation. Like, do I need a sample of 30 or do I need a sample of 100 if I want to have a certain margin of error and be confident within that certain margin of error? So what we want to do is we could solve this for n. So we can take E. So if I solve this for n, my first step would be to multiply both sides by the square root of n. Okay, so what did I do? I just multiplied both sides of the equation by square root of n. And then I'm going to divide both sides by E. Okay? And then finally, how do I get n by itself? Square both sides. So what is n? N is no, it's not n squared, it's n. Equals this thing squared. So this is if you want a certain margin of error and a certain confidence. So if you want to set your margin of error, say at 1 or 1.5 or something like that, and then you want to have that much confidence, say 95% confidence, well, we're going to use our 1.96. And we got our population standard deviation, and then set our margin of error. And if we do that, we'll get the sample size required to have this combination of margin of error and precision. Okay, does it make sense? Okay, so we did those already. So here's that formula again. I think that's what we got, right, when we did it ourselves? Good? Okay, so let's look at some of these here. D. Okay, so let me do some of this, okay? Let's go over some of this together. So I want this kind of by popular demand. So she's requesting number 2D. What else would you like to see? What's that? This one? So if I did 2D and the last one, would that be good? Okay, let's do that. Cool. All right, so we want a 95% confidence interval. So we already know what the z-score is for that. How many standard deviations are we talking about? 1.96. First 95% confidence, we want 1.96 standard deviations above and below. Okay? And then the sample size determined in part C. You should have gotten 97. Did you get 97? No, but what you got was 96 point what? All right, now so is 96 enough to get 95% confidence? If it's saying n needs to be 96.04, the point is that, so n has to be a whole number, right? You can't take a partial number of sample points. So do you understand that 96 will not get you 95% confident? It'll get you like 94 point something percent confident. So in order to make sure you have at least 95% confident, you're going to have to make that n 97. Okay? And what is our population standard deviation? 0.5. So we got what we need. Oh, and we got what's our sample mean? So our sample mean was 2.35. So our point estimate for the population mean is? What do we estimate the population mean to be? 2.35. This is our sample. This is the mean of our sample. Our best guess at the population mean is 2.35. But now with this other information, we can say, all right, so here's 2.35, and we're trying to be 95% confident that the actual population mean is within this interval. So how do we get the max of that? We're going to go we're going to go above how much? By the margin of error. So it's going to be 1.96 times 0.5 Right, so try to not make this memorizing a formula. What is this? We're going up 1.96 standard deviations above the mean, right? We're going 1.96 standard deviations above that. So that formula should make sense, and that should help you to remember it rather than just trying to memorize the formula, right? So we're going to go above the mean, 2.35 plus that number of standard deviations, and this is our standard deviation for samples of size 97. And then we're going to go, what? We're going to go that far below the mean, so 2.35 minus that number of standard 1.96 standard deviations. And our standard deviation for this size sample is 0.5 divided by square root of 97. So you're going to get your min. There's your min of the confidence interval. And there's your max of the confidence interval. And then the conclusion is we're 95% confident that the real population mean falls between those two. Or in other words, 19 times out of 20, when we do this procedure, our population mean will be in this interval. Yeah? Like this. So here's an example. Here's an example of writing a confidence interval, like that. Yep. So like they did it up in A64, from 456.4 to 608. That's how you declare a confidence interval. So don't get that confused. The length of the confidence interval would be the difference. But if they're asking for the confidence interval, you're reporting from the min to the max. That's how you report a confidence interval. Are we good on number 2, 866? Any questions on 8.66? Okay, so 867. Can I erase everything that I've written? So make yourself some room. Good? Okay, so 867, it says we want to estimate the mean age of all people. So population mean. We had a sample size of 2250. Is required to have a margin of error of 0.5 for 0.95% confidence. It says suppose that we can only have a sample size of 900. Determine the smallest margin of error given that the confidence level is to be kept at 95%. So that means that Z is 1.96, right? And we got a population standard deviation of 12.1. Okay, so how do we calculate the margin of error? How are we going to get the margin of error? What did we say it was? So again, to get our max, we know we're going to go x bar plus 1.96 standard deviations. So what's the margin of error? .96 standard deviations, right? So that distance from here to here is what we're adding to x bar. What we add to x bar. So that E is what we add to the number of standard deviations, or it's the times the standard deviation. So do we have everything we need? We got 1.96. We got sigma. Yeah. So it's just you're going to do 1.96 times 12.1 over square root of 900. So you're keep striving for making sense of everything, okay? That's going to be their best hope for success. If you just get locked onto formulas and just plugging in formulas without kind of making sense of it, that's it's going to make it harder, okay? Because if you don't remember the formula or you don't know which formula to apply, then you'll be lost. So really keep making sense of what we're doing. Are we good on these? Any more questions on these examples? We got one more thing to do. Last chance. Yeah, Kuzma. It's just saying that we want to minimize the margin of error, okay? And in these constraints, that's what the margin of error is. If you want a smaller margin of error, you need a bigger sample size, or you need less confidence. Does that make sense? If you wanted to make this margin of error smaller, you can't do it with a sample. You'd have to have a bigger sample size or relax how much confidence you have. Does that get it? Other questions? Okay, so the next section, 8.4, is what about all this stuff when we don't know this? So everything we've been talking about is if you knew the population standard deviation sigma. So it's kind of real. It's very realistic to say, why would we know that? We don't know the population mean. Why would we know the population standard deviation? Where would that, So what really is kind of more realistic is we don't know anything about the population. We don't know the mean, and we don't know the standard deviation, and all we have is the sample, okay? So if all we have is the sample, how can we infer what's going on with the population, okay? So what we do instead is this. It's very similar. So here's our confidence interval. Okay, so we have a simple random sample. We have a normal population or a large sample, but now sigma's unknown. Okay, so here are the assumptions. Before we said sigma was known, but if we think about that, it's kind of like, why would we know that, right? Why would we know that? We're starting with a population we don't know anything about. We're going to take a sample and try to figure out what the population mean is. So this is actually a more realistic situation now. Does that make sense? More realistic. You wouldn't know that anything about the population. So what we use then is the sample standard deviation. So it's the same type of setup, except now this is the sample standard deviation instead of sigma, the mean standard deviation. Okay, and so you notice something else is different too. What else is different? So what happens when you do this? When they do a distribution based on the sample standard deviation instead of the population standard deviation, the resulting distribution is no longer normally distributed. You can't use z-scores. It's a different distribution when you do this. Okay, so we use t values. So we're going to find these confidence intervals the exact same way, except that we're going to use a different chart because it's going to be a different, we're going to have a different distribution. It won't be a normal distribution anymore. And we're going to use the sample standard deviation rather than the population standard deviation. Those are the two differences. But then everything else is the same. Margin of error would be this part of it. How much you're going above the mean or how much you go below the mean. Okay, so let's take a look at an example. So we probably should. Okay, let me make this bigger. Okay, so let's take a look at this. So here we have sample size is 8.87. So we've got a sample size of 36, gave us a mean of 20, and a sample standard deviation of 3. And we want to come up with a confidence interval for the population mean for 95% confidence. Okay, so we're not going to use z equals 1.96 anymore. It's going to be some t value, right? So it's going to be some t value. So we need to go to the t-chart, and I'll post this on Blackboard. Okay, so again, we're going to do the same thing we did last time for 95% confidence. So what would that alpha value be right there? So if we want 95% confidence, so we got to think about we want a 95% confidence interval. We're interested in that right there. What percent would that be? He wants 2.5%. Agree with that? Half of 5%. 5% is going to be everything outside of the interval. So we want half of that. Okay, and then let's see. There's another kind of aspect to this, and it's called degrees of freedom. So our degrees of freedom is 1 less than the sample size. So there's this other issue of degrees of freedom. So what are the differences? The differences are we have the sample standard deviation rather than the population standard deviation. We have a new distribution that we're looking at, the t distribution, and we need to make note of degrees of freedom. It's going to be 1 less than our sample size. And if we want to talk about what that means, what that's about, you can talk to me outside of class, just because we need to get to the examples here. All right, so we've got that. What are we doing here? All right, so in that example that I showed you, what was n? 36. So how many degrees of freedom? Okay, so we got 35. So n equals 36, therefore 35 degrees of freedom. And that's df. And we want the t, so it's showing here alpha, we want that to be what? 0.025, right? So the 2.5% would be 0.025, and so we're looking right there. We want to get that value of t, because we want 0.025 to the right with 35 degrees of freedom. So we go down in the chart, and we see that that is right there. So this was in my column for t of 0.025 for 35 degrees of freedom. And so that's my value of t. So I'm going to go 2 above the mean, 2.03 of our standard deviation above the mean and below the mean. And that will do the confidence interval. So we got the 2.03. Where was our example? It's here. All right, so let's set it up here. Some room. Okay, so we had a mean of 20. And what are we going to get the top of the confidence interval? We're going to go 20 plus, what was our t value? 2.03 times our sample standard deviation over square root of n. Don't use the degree, truly use n there, okay? The degrees of freedom, 35, was just to find the t value. And then we're going to go the same amount below. So 20 minus 2.03 times 3 over 36, radical 36. Okay. So when you don't have the population standard deviation, you only have the sample standard deviation, that is a new distribution. It's the t distribution. And so to get our t, we need to use the chart knowing degrees of freedom and our confidence, but then the formula looks the same, right? So it's going to be the t-score times the sample standard deviation divided by the square root of n. And so then whatever this turns out to be. That's your max of the confidence interval for 95%. That's your min. Okay, so let's just look at one kind of application, and we'll be done. Okay, so here's one, Northeast commutes. It says 85% of working adults, more than 85%, commute by car. A sample of 30 commuters yielded the following commute times in minutes. So what do we want? We want to get a mean for all commuters in Washington, D.C. So you can hit StatCrunch here. So this is the multimedia, this is the textbook, so I can just do StatCrunch here and it will give me that data. And so what do we need about this data? We need the mean. So we're going to do summary stats, columns. Remember we did that at the beginning of the semester. So write this down. We have a mean of 27.97 minutes. N is 30. And our standard deviation is 10.0, we'll say 4. 10.04. That's what we need, right? So we've got our S value. This is our S. This is our X bar. And this is our N. So how many degrees of freedom? 29. So we got everything we need to put together a confidence interval. So we need to go here. And they want what amount of confidence? 90%. So we imagine 10% total on either side means how much just on the right? 5%. So we want T of 0.05 for how many degrees of freedom? 29. So t of 0.05, second column, 29 degrees of freedom, 1.699 is our t-score. And so now we can make this confidence interval. Ready? Oh, look at that. Is this what we found? 27 and 10.04? They told us it. Okay. Okay, so my pen stopped working at the end of class. I wanted to finish this example, or I could write actually. So we have a sample of size 30 commute times. We're trying to predict the population mean commute time. But we don't know, the whole point here is the population standard deviation is unknown. So instead we're going to be using, so we have our population mean, or sorry, sample mean, 27.97 minutes, and we have a sample standard deviation, and we're going to use that sample standard deviation instead of the population standard deviation, which means that we need the t distribution, not the z distribution. Okay, but the overall idea is the same as what we were doing before. We have our point estimate for the population mean, which we're using as the sample mean. And we're going to add to that a t-score times, now instead, the sample standard deviation over the square root of n is 30. So how do we get this t-score? Well, this is going to be t for a 90% confidence interval. That will look like this. I'll do it in blue. For a 90% confidence interval, that means we want to have 90% in here. And so that means the total of these outside two are 10%, or just this right here is our 5%, which is 0.05. So we want t of 0.05 will correspond to the 90% confidence interval. So we can look at a t-chart. Out of the way, okay. So, and we're going to look in here in column 2, and since n was 30, we're going to do 29 degrees of freedom. 1.699 is our t value for a 90% confidence interval, or 5% above that t value, and 29 degrees of freedom. So the upper bound on our confidence interval will be 27.97 plus 1.699 times 10.04 all over square root of 30. And then for the lower bound, this is a 10. 10.04. Okay, and then the lower bound will be, just like before, the mean minus 1.699 times 10.04 divided by square root of 30. That will give us the lower bound. So this will be 27.97 minus 1.699 times 10.04 divided by square root of 30. And so that will be this here will be the upper bound of the confidence interval, whatever that number turns out to be, and this will be the lower bound. Margin of error, same thing as before. I'll do it in red. Margin of error is this right there. And that will be how much we add or subtract from the mean. So it's kind of our distance away from the mean that we're, in this case, 90% confident that the population mean falls within that margin of error of 29.97 of the sample mean. Okay, so I hope this helps you with the homework.